Can you confirm you can hear me okay?
Yeah.
Thank you. All right, good morning, guys. Today we're going to do notes for 3.1. Okay, not going to be on the test tomorrow. Okay, we're just flip-flopping the days between yesterday and today. Yesterday was supposed to be the test. We flipped it to today, so we flipped it to tomorrow. So we're going to do 3.1's notes today. But I do want to make sure that you guys have an idea what's going to be on the test tomorrow. So related rates tests, open notes, calculators allowed, all formulas are provided. All right, so these are the problems that you're going to see. You'll see a Pythagorean theorem problem, a cone problem, cylinder problem, shadow involving similar triangles, L'Hopital's rule, linear approximation, and then either a volume paired with surface area, where you got to find the derivative of both equations, and you have to be able to plug in and find the missing piece of information, or area circumference, where you have area and circumference of a circle, find the derivatives of both equations, and trying to piece the puzzle together to figure out the missing variable. I've done various review sessions over Teams. I did one this morning, yesterday afternoon, yesterday morning, and I'll also do another one tomorrow morning, 7:15. All the ones that I've done there have been recorded, and I've just been going through various worksheets. They're all located on the related rates page, dated 10/1 through 10/9. All right, so if you look through them, there's all these various review worksheets. Along, want to get some additional practice with cylinder problems, you probably just look through and find all the ones that you want to practice with. Okay. Let's see what else. Yeah, so I've seen in the past where students get stuck on the problem and they end up losing time and potentially running out of time at the end. So let me talk about this, that not every part of the problem is equally weighted. So I want you guys to strategically focus on the parts that is going to be worth the most points, right? And those are the setup, the derivative, or setup, equation, derivative, right? So the final portion, like the Pythagorean theorem problem, where you have all the derivatives and values plugged in, and you're just trying to clean up that expression, that's minimal points, right? So you could still get an A and not answer, and not have an answer for any question, right? I'm looking at the process. I'm looking that you understand the process. The very final step of plugging in the calculator, rearranging fractions, and cleaning up, that's minimal, right? That's not as important. So I don't want you guys to be spending all your time trying to clean up your problem when it's only worth like 1 or 2 points, right? 15 minutes there is more valuable spent on the problem that you haven't started yet, right? So I think that goes specifically for problems that can be messy at the end, like cone problems, Pythagorean theorem problems, where you have all these numbers you have to combine. So maybe once you get to those points, maybe you just skip to the next problem, right? Because you know that you've earned, 80%, 90% of the points there. Just tackle the beginning and middle of the problems, and then the ends. If you lose points there, it'll be minimal, and you can still get a good grade, right? So. All right, and then if you have any, as you guys are reviewing for the test, if you come across a problem that you're doing that you're getting stuck on, feel free to message me through Remind, and I can help you through a problem, or I can reference you to maybe a video that I did of that problem and help you through it. Okay, so fourth period is a little bit longer. So tomorrow, the test is going to be released when the bell rings, right? An hour to take the test, and 10 minutes to turn it in afterwards. All right. One thing I want to go over is the new recovery policy. So I put in Teams this eligibility assignment for this test that you just took, 2.2, 2.5 recovery test. So we, yeah, let me go through. This is going to be due on Monday the 12th. So this new 89 recovery policy became effective for assessment, so basically tests and quizzes, starting September 21st. So this new policy applies with this recent 2.2, 2.5 test, but not the previous limits test or the 2.2, 2.3 quiz. So here, the maximum you can earn back is 70, but here and everything moving forward, you can earn back up to 89. However, there's a couple of conditions here. You need to let me know within 5 days to return the test that you want to request recovery. Either email me or send me a remind message to confirm that. And then you're only eligible to do recovery if you score a 79 or below on the test. Okay. But even then, you still have to do all these are a couple of things you got to do, right? So you have to attach every assessment. I've been including an assignment for that unit or for that assessment. So there is a 2.2, 2.5 assignment in Teams. So you have to turn in your homework, classwork, notes through that assignment. You have to do full and accurate test corrections, okay, to show that you're ready to do that recovery test. Now, if there's a problem that you're stuck on or the concept that you're stuck on, let me know, and I can always refer you to the part of the video in one of the classes that that I'm going over that topic, or I can schedule a time with you to work on that topic. And finally, there are problems from the textbook that you have to do, 10 through 80 evens, and that is in this link that I have, and it's all on Teams. So by Monday, this is going to be due by Monday. Okay, even though the recovery test is going to be on Wednesday, I need time to set things up and also to review your work. So once this is submitted, you'll be able to select one of the 2 designated retake times. You're going to send me which time slot you want. You can include your option to me either through email or remind. I need time to assign your time slot in Teams. You will need to take the full test if you want to do the recovery test. And then I will take the higher of the two scores between your original test and the recovery test. So the first time option is next Wednesday at 7 a.m. Okay. So the test will be released at 7 a.m. and then once you get started, I'll probably have the review session up so you can be on that live, be on that call. And then second option is 4:30 p.m. on the same day. Okay, and these are the only times. There's no alternate times. These are the only two times available for the recovery. Okay, so this process will be true for the remainder of this semester as well. Okay. We don't know what's going to happen next semester, but at least this will hold for this semester. All right, any questions with the recovery process? All right. Let's go to 3.1. Okay, so we're going to start chapter 3. So chapter 3, the main topic this falls under is curve sketching. So the idea is that we're going to work towards being able to look at a function, a derivative, and gather information about the graph. Critical points, where the graph has a max and min, the peaks and valleys of the graph, identify intervals of where the graph is rising, where the graph is falling, identify intervals of different curvatures of the graph. So we're gathering all these kind of physical traits of the graph through algebra, through calculus, and without the use of or creating our version of the graph based off of that information. So kind of falls under this category of curve sketching. So we're kind of working towards that. And the derivative function is going to help us gain information about some physical features of the graph. Okay, so today we're just focusing on the idea of max and mins, the highest and lowest points of a graph. And we're trying to do this, again, without, eventually being able to just find this information, relying on the function and the derivative, and not so much on the visual graph itself. But I am going to show the visual graph along the way so that we can kind of have an idea of what we're kind of aiming towards. All right, a couple of definitions to begin with. Extrema is just max and mins. So if you look at this point here, we call this point a relative max, relative maximum, or a local maximum. And the reason why is because if we compare this point to the points immediately to the left and to the right, it is higher than any of those points nearby. So if it's the highest point to the left and to the right, immediately to the left and to the right, we call that a relative or local maximum because it is the highest point in that restricted region. Okay. We call this point a relative minimum because compared to the points to the left and to the right, it is lower, it's lowest. So within this region, it's a minimum, so we call that a relative or local minimum. All right. And then this point here We also call it a relative max because compared to the points to the left and to the right, it's higher. So within this small region, it's the highest point, so relative max. But if we zoom out a bit, and if we look at the overall entirety of the graph, it is the highest point over the entire graph. So because of that, we can also call that an absolute maximum because there's no other point higher than that one, right? Not on this graph. So sometimes a point we can have it fall into two separate categories. All right, so visually speaking, relative extrema, relative max, relative min are basically any peaks and valleys or hills and valleys of the graph. So if you can visualize a continuous graph where there's a peak and valley, then you know those are relative max and relative mins. Now, when we talk about absolute extrema, the highest and lowest points over the entire graph, we have one here, right? But just to clarify, holes and asymptotes or infinity are not considered absolute extrema. So here's an example. So normally we would say that's a relative max, but there's a hole there, so no relative extrema. At holes or asymptotes. So if my graph looks like this, right? Infinity is not considered absolute max, right? So we don't have, there's no absolute extrema here, and there's no absolute extrema here either. Okay, let's look at closed intervals. So closed intervals is where we have endpoints defined, and everything is connected between those endpoints. So here, if we look at this point here, we also consider this a relative minimum because within this region, it is the lowest point. And an absolute minimum because we don't have a point lower than that, right? So this, we call that absolute minimum. Now this point is the absolute maximum because it's the highest point over the entirety of the graph. But we don't call this a relative max because this is not the hill of a graph. There's nothing to compare it to. I need this point to be higher than a point to the left and to the right. There's nothing for me to compare it to on the right. So this is not a relative max or relative min. So keep that in mind. There's no relative extrema at endpoints. The only thing that it can be is an absolute max, but it has to be the highest point overall. Okay, the next thing is on an open interval. Let's say we had holes on as our endpoints. So if we look at this point here, it is still the relative minimum. It is still absolute minimum. But this is now a hole, so this is not considered an absolute maximum. Let's say this ordered pair, let's say the hole has ordered pair at 3, 4. Even though it will get infinitely close towards 4, we're not able to pinpoint a specific number that is higher than everything else, right? So if I choose a point really close, let's say 3.999, right? I can always turn around and find a point even closer, right? Even higher. So we can get infinitely close towards 4, but we're not able to pinpoint a specific number. So we say there's no absolute maximum here. All right, I'm going to read through these notes here, and then I'm going to give a visual representation of what we're trying to achieve, and then we'll do one or two examples. Okay. All right, so here's our main topic for today, which is extreme value theorem. So extreme value theorem is telling us that if a function is continuous on the closed interval, right, no holes, no asymptotes, no breaks, then it has both an absolute minimum and an absolute maximum on that interval, guaranteed. Okay, so to determine that, we have to consider our candidates. So absolute extrema, the highest and lowest points, will either be at critical values or at endpoints. So let me talk about what critical values are. Critical numbers are x values in the domain of a domain of a function where the derivative of a function is either 0 or undefined. So basically, slope 0 or slope undefined. Okay, relative extrema only occurs at critical numbers, but not all critical numbers are where relative extrema occurs. Okay, let me show you a picture to demonstrate that. So if you look at this graph here, all right, we have critical points wherever the slope is 0, right? Here's 3 of them. These are all critical points, slope 0. But not all of these are relative extrema, right? So this one is, right, that's a relative min. This one is, it's a relative max. But here, this is neither a peak nor a valley. So it's a critical point, but not all critical numbers are we going to be able to guarantee relative extrema. So and then another point to make is max and min values refer to the y values at that point. The emphasis at the y value, we will explore that within our examples that we're going to see. All right, so I want to summarize this in a diagram, in a picture I'm going to show. So this handout is also, I think I have it under 3.1, 3.4 summary sheet, and I have this link. So if you didn't print this out, that's fine. You kind of just follow along and print it out later. Okay, so here is what extreme value theorem is going to do for us. Is what we can do, what we can find. Or the purpose is we want to find the absolute max and absolute min, the highest and lowest point on the closed interval. Now, obviously, if you have the graph in front of you, then picking out highest and lowest points is not hard. But we're trying to do this being blind to the graph and just relying on function and derivative. Okay. So the first thing we need to establish is our function continuous on the closed interval? So can we guarantee there are no holes, there are no asymptotes, that there are no breaks? And the way we look for it is we look in the denominator of our function. Now, sometimes it may be okay to have asymptotes and holes as long as it falls outside the interval. So we always have to pay attention to the interval. We only care about what's inside our interval. Anything outside, we can care less. So as long as our interval is protected, then we can conclude that our function is continuous on the closed interval. The theorem is going to apply, and we move to the next step. So the next thing that we do is we find critical points, right? Let's say, so here's a visualization that I want to show you. If the graph looked like this, the only places that the graph can achieve a max or min is at the endpoints or at critical points, right? Imagine these points were shortened. You can imagine how this can all of a sudden become the absolute max, and this is already absolute min. Or if I extend this line further down, I can see how this could be, the endpoint could be absolute min. So when we find critical points, we find potential candidates for absolute max, absolute min. So the way we find critical points, we find the derivative, and then we set the numerator of the derivative equal to 0. And if there's a denominator, we also set the denominator of f prime equal to 0. And this is what the numerator does for us. If I set the numerator of f prime equal to 0, I'm able to locate places where slope is 0, such as this point, and we're able to understand this is a candidate for our potential absolute max. But if there's a denominator, we also need to set that equal to 0. Even though it's a place of slope undefined, here's the visualization, right? A slope undefined could also be an absolute minimum or absolute max, right? So we don't want to forget about denominator of a derivative, if there is one. So let's say we found these critical points, -1 and 2, and then we also consider endpoints of -3 and 4. Then we're going to take all those critical point x values and we're going to put them into the function and information about their y values. When we do that, f of -3 will give us 1. Let's say we got 1, 5, -3, and 7. And then we just spend the time to compare those y values. The highest y value is going to be your absolute max. The lowest y value is going to be your absolute min. So here we can tell the absolute max is 7. Absolute min is -3. And we're going to practice writing it out this way so we can emphasize the fact that the y value is more important than the x. The y value is more important than the x. Okay, so I'm going to constantly refer back to this diagram as we do our examples so you guys can kind of see the steps and where we're headed towards. Okay, so let's go to the second page of our notes and let's look at example 1. So example 1, find all critical numbers for each function. What are the values of absolute extrema? So we want to apply extreme value theorem. The first thing we have to consider is, do we have any continuity issues with our function? The nice thing here is we are dealing with a polynomial. Polynomial, smooth curve all the way through, no breaks, no asymptotes or holes. So we're going to have to make our statement about continuity. So we say our function is continuous on the closed interval. So we say our function is continuous we've worked with continuity conditions before, right? Remember intermediate value theorem, EVT? So on the test, on that chapter 1 unit test, if you didn't include continuity statement, I took off a point or took off 2 points. If you say continuous everywhere, but you did not include your interval, I took a point there as well. Okay, so this is going to be the condition that we're going to need for every theorem that we see. We're going to see, right now we're doing extreme value theorem. We're going to see Rolle's theorem. We're going to see mean value theorem. We're going to see average value theorem. It's all the same, right? So just know that if you don't have the conditions in place, just like in the future, I'm going to be taking off points. Right? So let's get in the habit of writing out those statements and then understanding we need to include our interval as well. All right, so the continuity condition has been passed. We know we can move on with the problem. So our next step is we're going to focus on, these are the endpoints, right? We know we're starting at x value of 0. We're ending at x value of 2. We know we're going to be testing endpoints. We know these are candidates for absolute max, absolute min. But we also want to know, are there any critical points that's between that we need to involve as well? Okay. So we're going to find critical points. We're going to find f prime and set f prime equal to 0. We're just going to be in search of places of slope 0, because slope 0 could end up being an absolute max. But in this case, our problem is a polynomial, so there's no places where slope is undefined. So for our problem, for number 1, b is not going to be an option. We don't have to worry about b. We just have to worry about setting our numerator or our derivative equal to 0. All right, so let's find f prime. So power rule, right? What's the derivative of f prime? Or what's the derivative of f of x?
12x cubed.
Good. 12x cubed minus 12x squared. Okay, so this is where we're going to be looking for critical values. We're going to set our derivative equal to 0 and solve for x. I can factor this out, right? What's the GCF that I can take out? 12x squared. Okay.
12.
So I can take out the 12, and I can take out x squared, and then factor the rest. I can set both parts equal to 0 and look for critical points that way. Divide by 12, take the square root, add 1 to both sides. Okay, we have a duplicate, so we only have to test 0 once, right? So we'll test critical point 1. So we'll test 1, and we'll test 0, and we'll test 2. And between those 3 values, whatever is the highest is the absolute max. Whatever is lowest is the absolute min. Now, can you think of an instance where we may not use a critical point? What do we have to be careful with? Okay, it's true, right? But we should be able to establish that before we get to this point, right? Something else. When do we not use a critical? When may we not use a critical value? Or when may we not test a critical value? Okay, let's talk about location. Where does critical value have to reside?
Inside the on like when it's
right inside the interval, right? So yeah, we gotta keep that in mind, right? Gotta be careful. We gotta have understanding where our range is, right? Sometimes we may end up with critical values that's outside. If that's the case, we're not going to use it. Okay, our interval is key. Same thing with IVT, right? IVT, we may end up with, we found critical values that's outside, we didn't use it. We only care about the interval. Okay. Anything outside the endpoint is not part of our problem. But 1 is safe, right? 1 is nicely between 0 and 2. So we'll test our endpoints and we'll test 1. So this is our next step. We're going to test critical points and plug them into the original function. And then we'll compare their y values. Highest y value is your absolute max. Lowest y value is your absolute min. All right, make sure that you're plugging this into the original function and not into the derivative, right? The derivative is not going to give us location. We're looking for location now. So 0 plugs in for x. Same thing, plug 1 into the function. Plug 2 into the function. So 3 times 16 is 48. 4 times 8 is 32. Okay, so now our attention is focused directly on these numbers. These are the numbers that we're going to use to determine absolute max and absolute min. All right, what's the highest number that we see? 16. So we're going to write it out this way to help us remember the emphasis is at the y value. So we're going to write this. Absolute max is 16. Less important is the x values, but we're still going to include it. But if we write it this way, we can remember that it's really the 16 that we're concerned about. But it's nice to have the location as well. Okay. What's the lowest y value that you see? -1. So we say absolute min at x equals 1. Okay, any questions with that? And the reason why I want us to write it out this way, in the textbook, you may see them, you may see answers like this. They may say absolute max is 216, and then absolute min is 1, -1. But I don't want us to write it this way, because on the AP exam, if they ask you for the max value, they're looking for the y value and not the x. So I'm trying to gear us towards how AP exam is, how they want the answer to be, how for us to interpret the question. So for instance, on the AP exam, maybe they say this, what is the absolute max value? And they give you a couple of options if it's multiple choice. Let's say they gave you an option of -1, 1, 16, or 2. Then the correct answer is going to be 16, even though the order pair is at 216. All right, sometimes students may look at this going, well, both are correct, right? But think of max value as what is the max height, right? If you're looking at the height, you're looking at the y value. So the focus is on the y value and not so much the x. All right, any questions with that concept? So that's why I want us to write it out this way. Kind of helps us remember the focus is on the y value. Okay, let's do one more here. Number 2. We have our function x minus 1 to the 2/3. This is kind of a strange exponent. We want to consider continuity issues. And if we think about this function, normally radicals gives us issues in terms of negative numbers, but this is a odd degree root. So odd degree roots is not going to present issues for us. It's the even roots that's going to cause issues in terms of we can't have negative numbers inside a square root or even root. But odd root is okay. Our function is continuous everywhere. There's nothing that makes this undefined. So we can make our statement. Our function is continuous on the closed interval from -1 to 0. Make sure that you're not only writing out the continuity statement, but then you're also specifying your interval. All right, we have our first our condition, passing with no issues. Next step, we want to find critical points. We want to find f prime, okay? And then we now may need to consider both top and bottom. Right? So here's our function. We want to find the derivative. What method do we have to involve to find this derivative?
Chain rule.
Chain rule, right? There's an outside portion, there's inside portion. I can't expand this out. This is stuck the way that it is. So we have to apply chain rule. So there's an outside portion, there's an inside portion. Outside portion is the parentheses to the 2/3. Inside portion is the x minus 1. All right, we take turns with each of these derivatives. What's the outside derivative? All right, what's power rule there?
2/3 to the -1.
To the negative 1/3, right?
1/3.
Right, subtract 1 from the exponent. And we keep the inside unchanged, untouched. So we took care of the outside derivative using power rule times, what's the inside derivative?
1.
Just 1, right? So it's not going to change anything, but I want to remind us of our chain rule steps, right? Outside derivative followed by inside derivative. Okay, let's clean this up and see if we can find our potential critical points. I'm going to place the numerator where they belong, the 2 above and everything else below. The 3 goes below. The x minus 1 to the 1/3 goes below. All right, we have our f prime. And now we're going to use our f prime to find our critical points. So we're going to consider the numerator and also consider the denominator. So numerator, am I going to have any critical points from the numerator? Right, if I set 2 equal to 0, that's not going to make sense, right? There's no variable up top. So I looked, but there's nothing to find. Denominator has a variable, so we're going to look in the denominator as well. It may give us a place where the slope is undefined, but slope undefined is still a candidate, potentially, because if it's a sharp turn, we don't want to forget about sharp turns, right? It could end up being an absolute max or absolute min. So we don't want to forget about that candidate. So we'll set the denominator equal to 0. Divide by 3, cube both sides. Okay. So if I raise both sides to power of 3, I can get that 1/3 to go away. So all this work, I found a critical value. Are we ready to use this as our candidate for extreme value theorem? So there's an issue here, right? I mean, we found everything correctly. We did all the steps right, but here's our interval, right? We only care about values between -1 and 0. So 1 is outside the interval. It was the critical point. It would work if our interval was a little bit longer, was a little bit wider, but doesn't include this point, so this is outside the interval, so we don't use it. So just be aware of that, right? Sometimes you may find critical points that's not used, and if that's the case, we still continue with the process. It's just that we only have 2 candidates, right? We only have endpoints to worry about now. So we'll plug -1 into the function, we'll plug 0 into the function. One will be the absolute max and the other will be the absolute min. Okay. So we'll plug them in. -1 first. I get -2 squared, which is 4, and the cube root of 4. Okay. It's some decimal value, right? Plug 0 into the function. So 0 minus 1 to the 2/3. So -1 squared is 1, cube root of 1 is still 1. All right, we have our candidates here. We're looking at this number and we're looking at this number. So what can we conclude? Absolute max value is what? These are close. These are really close, but cube root of 4 is a little bit larger, right? Yeah, cube root of 4 is 1.58. Okay, so absolute max is cube root of 4. So that's the important information, right? The less important information is the x value, but we can put that to the side. And the smaller value is the 1, so we call that the absolute max. Sorry, absolute min.
Mr. Yang, how did you get cube root of 4?
Right, cube root of 4. So I took -2 raised to the 2/3. So -2. So whenever I see a number raised to a rational exponent, I can always do these separately. So I think it's easier if I just took care of the numerator first. So -2 squared is just going to be 4. So that's the same thing as now 4 to the 1/3, which is cube root of 4. So I'm kind of breaking this into smaller parts. But if you enter this in the calculator with the parentheses, you should come across 1.58 as well. Just make sure you use parentheses if you want to do that. Oops, -2 to, sorry, to the 2/3. All right, so absolute minimum is 1. The less important information is the x value, so we'll put that to the side. Okay, so this is the way I want you to express your answer. Emphasis at the y value, but include the x value just for additional information. All right, any questions? There's a bit of homework with this section, and that is, I have that PDF file under homework for today's link. It's just the first page. The key is attached, but I just picked out problems. I copy and pasted problems from the textbook 19 through 28, so those 6 problems. But more importantly, I want you guys just to get ready for the test tomorrow. Okay, any final questions about the test? All right, that's all I have. Have a great day, and study for your test. And I may see you tomorrow in the help session. Yeah, have a great day, guys.